This morning we are going to see a new technique called the design via root locus. And based on the concept of the root locus method, we are going to design a control system. So the first thing we're going to do is to review what the root locus is and how that could help us change the system the way we would like it um, to control the control to be implemented on the system. So take a look at the example that you see on the screen right now, and you will see that you have a, you have a transfer function. Let me see. Let me go over here. Let's say that you have the plant first of all, and then you have a feedback loop here, and then you can have a control system here. We could actually do the simple loop in such a way that the controller is just K. So let's see, we could just do a simple block diagram, or you K, instead of K, you could have this other two blocks, which we would be some sort of a control system, like this could be K and this could be something else, and combined they would modify the plan. But what I'm trying to say is that if we were to go to a simple loop, all right, like for example here, we could just draw a simple control system that we have in this yeah, we're gonna go with this pen. um, you have a simple loop like this where you have the gain K and you have your transfer function. Just as an example, you could have something like transfer function, something like S plus B, something like this, just for example, yeah. And then this has a feedback control system like this. So the question is, what is the response of the system? This is your system. If K changes from 0 to infinity, every time, every point or different value of K is going to have a different value of the root locus. So for every value of K, you will get one position on this graph. So when K is equal to 1, you see you have this pulse right here, this thing. When K is bigger than 1, then they become here on the blue line, and they come in pairs. So if one is here, the other one is right here. And if you keep going here, you see you could go to the right hand side and get in an unstable situation. So yeah, so that we have a okay, so for every value of K, you get a position on the blue line. So you see, if you change the value of k, you should be able to, if you change the value of k, you should be able to obtain a position of on the root locus like here, yeah, and you keep increasing, you'll get the pairs like that. At some point you're going to get this value, which is the limit, and here you see that the system is going to respond with oscillations forever like this. But if you go over here, you know, if you go to the right hand side, your system is going to do this, and then it will blow up like that. See? So you do not want the roots to be on the side, but every time you change k, you can only stay on the blue line. The question is, what do you do if you want the roots to be here? That is the question. Okay, so what we're going to do is, we have your system, the plan is also your system here. Okay, and can we do some control scheme in such a way that you have this this could be just your k, all right? Or can we put another compensator, like for example 1 over k, another k, 1 over s, and the combination of these two would act on the system. Now this is your controller right here, okay? This is your system, but also the feedback signal could actually be affected by some feedback compensator. To make life easier, we could start by analyzing it when this is equal to 1. So if you have a transfer function like this, simple loop like this, and you get the you get the roots here, yeah, to begin with, and as you change it, those roots would move on this. See, one of them is going to go this way. See the blue? Let me just put the one position that I think would be here. This one would go here. These two move inside, and maybe they go here, see? And if you increase the value of k to another position, you'll get one here and the other two here, see? That's this system. But if instead of doing this, we add, like I said a moment ago, to this, you add, let's say, a block that is 1 over s, and then you have your k block in here, and then you have this g of s like this, which is your system, and then you get a unity feedback loop like this. What happens is that in here, this gets combined and it will be called like this, see? So the product of those two is k divided by s. So this is obviously 1 over s is an integral control. 1 over s is integration. What has happened if you do this to the system? You see this? What has happened in here is that you have created now a new way. See, the roots would move. 1 over s is at 0, s equal to 0. So one position would be here, the other would be the other there's gonna be 2, and the other one would be here, one would be here, and another here. See, now we have to keep track of 4. And if you keep increasing the value of k, you will get 1 here, 1 here, 1 here, and 1 here. 4 roots. So you see, everything is cool. There's no problem if we increase the value of k, but look what's happening here. This eventually will go like that, see? And there will be a critical value for k where you cannot go to, you don't want to go anymore because you're going to the right hand side. That is what we would like to do. We would like to see how the system responds if we change it. Now, if you add something to it, remember that the controller was, on the previous one, was k over s, right? But if you add something to this, instead of just k over s, let's say you differentiate and add another, see here how it is, right there, see? Yeah, so in here you have this differentiation, see, and then you add a constant. So you do something more to the system, something different here. So your this is the result of you could say that the block here is s plus a, like that, and then you have k, and then you have 1 over s, see? This is your controller, and before your system g of s, like this, see? Yeah, like this. So this right here is this. So when you see the word compensator, is another way of saying control. So in this case, when you add this factor like this, the roots of the numerator are called zeros. The roots of the denominator are called poles. So, and the way we do it on the graph is, see, you draw it like a 0. So in here, when you change this, you are starting with the poles here. Now you need to keep track of 5 things. Here, the 4, and then the 0 here, this one. So if you change the value of I would think that if you change the value, you would move this way for that one. This one and this will come in, and this will go out like that. But this 0 makes it in such a way that this has been modified. Now, granted that there will be again some value in here, some value when is the so-called crossover frequency, for some value where the system would become in the border of being unstable. If you go to the right hand side, it will definitely become unstable. So I think it would be a good idea for us to take a look at this example right here. This one has numbers. So you see, this is your transfer function here. This would be the compensated transfer function. So this would be just starting with the proportional control, which is what the root locus does. And so this whole thing, like that, that is a block that would, as far as the computer is concerned, this is going to be like this: k divided by s plus 1, and then s plus 2, then s plus 3. No, s plus 10, excuse me. Yeah. And this one in here, if we add this, yeah, I mean, the block becomes like this. Okay. And this other one in here, we have added the derivative control. This transfer function for this system is going to look like k. The numerator is plus 0.1, and then you'll have the bottom one, which is plus 1 times s plus 2 times s plus 10. See, these transfer functions that I am drawing in right now is what we need to enter in MATLAB to be able to see how this changes. See? So I would like to propose that we go to MATLAB and we're going to see this kind of curve. So you have the uncompensated system, which be this one first, and then you have the compensated system. But I think it would be best if we actually do it. So the idea is that if you take the response, it would be the uncompensated system, and the blue would be the compensated system. So you change the behavior of the system by doing this. So I think I would like to go back here, and then maybe we'll go directly to MATLAB in here and actually run that program and put these transfer functions into it. So what I would do is, let me move this one over here. Let's free ourselves so these other unnecessary windows. And let's get on MATLAB to doing these two transfer functions. That's going to be our mission right now. So I think yeah. So as soon as MATLAB comes in, I'll show you how to enter these transfer functions in MATLAB. Now, of course, if you use the CAMG to produce the transfer functions, CAMG will deliver already the transfer functions to MATLAB. So in this case, we are going to look at the two transfer functions that we have on the screen there, and we will look at the first one, which would be just the variation of the gain, which is the concept of the root locus, and then we will put the second one and we'll see the difference. So in this case, let's get over here, and This is going to be a problem. Let me try to see if we do it as, there we go. We need to enter the transfer function uh, in MATLAB. So the first thing, one thing that I have found that is easiest to define the variable s as a transfer function of the, I think we go and we say quote, let's see, s like this. In other words, we make s a variable that is a transfer function, continuous time transfer function. Once we have done that, we are able to enter the, let's say, the numerator is going to be just 1, right? So this is 1 like this. Yeah. And the denominator, if you do what I'm doing here, it makes it very easy to enter this. And we don't have to resort to polynomials or anything like that. So s plus 1 like this. And then you have, of course, we'll have to say multiply by s plus 2. Yeah. And then we have multiplied by s plus 10. Yeah. Let's see how this does. This is my denominator here, you see. So now the transfer function g is easy to say that g is the transfer function of the numerator and the denominator. Yeah. And then we have okay, there is something went wrong in here. I think we go to the denominator. I believe we have to get this polynomial like this. We're missing a couple of parentheses in here. Let's give it a try again. Very good. So now we're going to go to this one and to define the transfer function of the okay. What's the value of g in here? What I want to see is the transfer function. G is supposed to be a transfer function now. Because we will have to. Okay, I think we have. Yeah, I have made a small mistake in here. I believe we have to do the command poly for polynomial, and I believe that's what I'm missing here. It did not understand the I think even Okay, let me give it a try now. It doesn't want the. I don't believe I have a unbalanced parenthesis, but it might. What we need to do is to define the transfer function as a. So we have in here this situation, this transfer function, and we have this other transfer function. The first one, this one, will have a root locus like this. See, you have the ability to look in what position the system will become unstable, but also you in MATLAB, if you click on the root locus, it will give you the damping ratio, it will give you the value of the root, and will give you the value of k. And that's what I'm trying to say in designing this with the root locus. But if you go this route, you're going to have this 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 root locus in here. So in this case, you will see different values of k that you can operate before the system goes unstable. And what you'll see is that in one case, the uncompensated system will respond like this, but the other one that has the control, the second one, it will respond like that. So depending on what you want to do, you can actually put one compensator or another.